So the topic of this video will be phase diagrams. I have drawn two phase diagrams up here. I want to discuss what they tell you. Basically, it tells you at what temperature and pressure the phase of matter for your material will manifest itself as. So, for example, the most familiar material to all of us is water. So, water under normal conditions is a liquid. It does evaporate some, but it doesn't boil until it reaches 100 degrees C. It doesn't freeze until it reaches 0 degrees C. So on these graphs of temperature versus pressure, if you were to change the temperature or the pressure, then you'll be at different places on this graph. And so there is a solid phase, there is a liquid phase, and then where I put steam is just the vapor phase of water. Doesn't mean it's necessarily hot. As a matter of fact, water vapor can be quite cold. Anytime you're just below this, you're in the vapor region, where vapor is the most stable form of water. This is the most stable form being liquid, and this is the most stable form being solid. And so these scales will be temperature. It's not linear in any way whatsoever. And this is going to be the pressure in atmospheres. It's not going to be linear in any way whatsoever. So these curves here are called phase boundaries. Now, anywhere on this boundary, you can have the two phases in equilibrium. So if you were at this particular pressure and temperature, you could have water at that pressure and temperature, or you could have vapor at that pressure and temperature, or any mixture of one or the other, and they wouldn't convert one to the other. They'd be in equilibrium. Now, for the special case where it's one atmosphere, when we have liquid water in equilibrium with water vapor at one atmosphere, we call that boiling, and that occurs at 100 degrees C. When we have liquid water in equilibrium with the solid, that's going to be the solid liquid curve, where any point on this curve they're in equilibrium. But at one atmospheric pressure, that equilibrium occurs at 0 Celsius. What that means is you can have ice at 0 Celsius, or water at 0 Celsius, or any mixture of ice and water will be at 0 Celsius, and they won't change from one to the other unless you add heat or remove heat. Now there is one point where all these curves intersect, and it's called the triple point, and there's absolutely no flexibility. Here you can change the pressure and temperature and still be on this curve, but this triple point has to be exactly at 0.01 degrees C and at 0.006 atmospheres, and you can have all three phases of water in equilibrium at the same time. One of the more interesting features of phase diagrams is that you should be able to find yourself, we're given the x and the y coordinates, the temperature and the pressure, find out what phase is most stable for you. And then if you say, well, let's change the temperature, if we cross the phase boundary, if we do, then we'll change the phase. For example, let's take one atmospheric pressure. At a low temperature below 0 C, we warm up. Well, we're not going up and down in pressure, we're staying one pressure of one atmosphere. Then when we hit 0 C, start to melt and become water. Then once it's all melted, now you start raising the temperature of water, and then you reach another point at 100 degrees C where water converts into vapor, and then your water boils. You can also make changes by changing the pressure. So if you take an ice cube and say you're right here at this temperature and pressure, and you increase the pressure, eventually you'll melt the ice. So ice under high pressure melts, and that's very evident if you watch ice skates on ice or something like that. And that's actually quite unusual behavior. Usually the slope between solid and liquid is such that apply pressure, the solid is made from the liquid rather than melting the solid. Okay, so now there is one temperature above which you can no longer tell the difference between vapor, which is a type of liquid, or type of fluid, or water, liquid, which is also another type of fluid. So both gases and liquids are fluids, that is to say they don't have definite positions for all the atoms or molecules, but above the critical point, this temperature and this pressure, they kind of merge into each other continuously. You don't see any sharp transition like you do at some of these other places. So with ice and water, you see a definite point at which ice starts to melt, and then you can tell the difference between the two. But you can't tell the difference between the liquid and the gas under very high pressure because they look very similar. There's no sudden change in the size or the density or other physical properties. Now CO2, dry ice, that's familiar to you because it doesn't melt. It's dry. And so that point at 1 atmosphere, that temperature is minus 78.5 degrees C. Well, dry ice is very cold for that reason. But you see if you cross this line, you go from the solid to the vapor directly. So the liquid solid line occurs at higher temperatures and higher pressures. And so the pressure has to be at least 5.11 atmospheres before you actually even see liquid. And so if you buy CO2 in a tank, you can actually hear liquid sloshing around because it's been filled up with the gas under high pressure and it turns into liquid under high pressure. So you buy the CO2 gas and puts into a tank in high pressure and turns to a liquid. And I suppose if you pressurize it enough, you could eventually turn it solid, but nobody wants a solid inside their tank. And CO2 actually has a critical point as well. And there's something called supercritical CO2 extraction. For example, you can take caffeine out of coffee beans with CO2. CO2 is nice and inert and harmless as far as chemistry goes. And so some people find that preferable to other solvents that remove the caffeine from coffee.